Greetings, dear students. In this particular video, we are looking at revision of GCE Ordinary Level Physics. Revision of GCE Ordinary Level Physics. And we will start with physical quantities. This compilation is made up of two main parts. The first part covers work from Form 1 to Form 3 and part of Form 4. And the second part covers Form 4 and Form 5. So this video is for the first part. We start with the first chapter, which is on physical quantities and motion. What is a physical quantity? It's a quantity that can be observed and measured. For example, time, mass are all physical quantities because you can observe and we can measure them. But qualities or quantities that cannot be measured are not physical quantities. For example, you can see that somebody is happy, you can observe it, but you cannot measure the amount of happiness in terms of physics. Sadness, poverty, anger, and hunger or bitterness, these are all physical quantities that can be observed, but you cannot measure. So these type of quantities are not physical quantities. Okay, so these qualities are not physical quantities. And examples and units of physical quantities, normally there are 7 basic or fundamental physical quantities from which all the other physical quantities that exist are derived from. So the 7 basic physical quantities and their SI units are, we have length. Length, the symbol for length is L, and the SI unit of length is the meter. We have mass. Mass, the symbol for mass is M, and the SI unit is the kilogram, kg. And then we have time. Time is small t. The SI unit for time is the second. We have electric current. The symbol is I, which is the ampere. And the SI unit is the ampere, which is having a symbol A. The symbol for ampere is A. Then we have temperature. Temperature, the SI unit of temperature is the Kelvin. So whenever you have calculations to do with gases, especially, if they give you the temperature in degrees Celsius, you have to convert to Kelvin. And the symbol for Kelvin is the K. And then we have the amount of substance. The symbol of amount of substance is N. And the SI unit for amount of substance is the mole. And the unit for mole is MOL. You equally have luminous intensity, LV, whose SI unit is the candela, capital C, small d. All these are the 7 basic or fundamental physical quantities from which all other quantities are derived. For example, examples of derived quantities are area. Area, which is measured in square meters, that is meter times meter. We equally have density, we have weight, velocity, mass, we have pressure, we have volume, and a lot more. All those are derived physical quantities. And one other important thing that we have to understand in calculations is what we call the prefixes, which are used for numbers. Okay, so like 10 to the power 12 is the tera. The gig, like the gigabyte we talk about all the time, the giga is 10 to the power 6, kilo is 10 to the power 3, milli is 10 to the power minus 3, micro is 10 to the power minus 6, like microcoulombs, nano 10 to the power minus 9, and pico is 10 to the power minus 12. As you continue to watch this video, don't forget to click on the subscribe button, where you are going to promote us and make us also happy in bringing out quality content to help you in your examinations. And equally, we have conversions from seconds to minutes and all of this. You have to know that 52 weeks make 1 year, and 365 days make 1 year as well. One important conversion is from the kilometer to the mile. We know that 1 mile is equal to 1.2 kilometers. This one is very important. Then for temperature and mass, for mass, 10 milligrams make 1 centigram, 10 centigrams 1 decagram, 1 decigram, 10 decigram 1 gram, and 1000 grams 1 kilogram. A ton is equal to 1000 kilograms, or a ton is equal to 1 million grams. Then to convert from temperature from degrees Celsius to Kelvin, we use the formula temperature in Kelvin, this is this T, is equal to temperature in degree, that is theta, plus 273. And we can do transposition with this formula to get the temperature in degrees Celsius. So the temperature in degrees Celsius should be equal to temperature in Kelvin minus 273. Equally, to convert from Fahrenheit or from degrees Celsius to Fahrenheit, we use this formula to convert temperature from degrees Celsius to Fahrenheit. And the formula is temperature in Fahrenheit is equal to 9 on 5 times the temperature in degrees Celsius plus 32. Still with Form 1 work, or Form 1 and Form 2, Form 3, these physical quantities have their units or measuring instruments. They have their measuring instruments. After we have seen the units, they have their measuring instruments. For example, time is measured with a stopwatch. That's the main measuring instrument. Can be measured with clock, watch, and so on. But the main instruments for measuring time in the laboratory is a stopwatch. So that's what you should give. Then mass is measured with the mass balance. Though equally have other balances for mass. But the measuring instruments in the lab for mass is the mass balance. Then length is measured with a tape or metal rule in the laboratory, a tape or metal rule, but in the lab they mostly use the metal rule. Then temperature is measured with a thermometer. And of course, we have all of these few conversions here. You can have these notes that I'm going through like this. You can have these notes by going to the website www.gcepreps.blogspot.com, or you go to www.gcemathspanel.blogspot.com. So here are some few plane figures and their areas. We'll not focus on this because we know you have gone through this in mathematics. Let us move to motion. What is motion? These are some of the first questions that you find in your GCE paper. And motion is defined as the change in position of an object with respect to another object in a given time. Motion is defined as the change in position of an object with respect to another object in a given time. For example, a car moving along a straight road is in motion. The moon going around the sun is in motion. So I give credit. This work gives credit to Mr. Chi Christopher of GBHS Bamenda. We equally have Mr. Tata Gerald of GBHS Bamenda, who have been pioneer teachers who have really molded a lot of students for years past. We equally have other teachers like Mr. Akaba and a lot more. All right, let us look at a car moving along a straight road. Is the car in motion? Yes, so they may ask you to define motion and give an example. So motion is the change in position of an object with respect to another object in a given time, and an example is a car moving along a straight road. The moon going around the sun is also in motion. And then we have speed. Speed is the distance traveled in a given time, or distance per unit time, and is measured in meters per second. Larger units of speed are the kilometers per hour. The mathematical expression for speed is speed equals distance traveled divided by time taken. And from this mnemonic of a timetable, we can do calculations for time if given speed. For example, if given the distance to find time, time will be equal to distance divided by speed. Now, if given both the distance and the time to find speed, speed is equal to distance divided by time. If you are asked to look for distance, distance is equal to speed times time. And equally, to convert from kilometers per hour to meters per second, so that is, we move from this direction to this direction, we multiply by 5 on 18. Why are we doing this? Because we know that the kilometers per hour is the same as 1,000 meters over 3,600 seconds. So this is the conversion of kilometers per hour to meters per second. Then to convert from meters per second now back to kilometers per hour, we multiply by the reciprocal of 5 on 18. That is, we multiply by 18 on 5. And let's look at this example. A boy covers a distance of 200 meters in 25 seconds. Calculate his speed. So the speed is just distance divided by time. So 200 meters divided by 25 seconds gives us 8 meters per second. Don't forget to put the units, meters per second. A train travels at a speed of 160 kilometers per hour for 5 hours. Calculate the distance traveled. We don't need to change these kilometers per hour to meters per second because they just need the distance. So this distance traveled will just be equal to speed times time. Speed times time. That will give us 160 kilometers per hour times 5 hours, which is 800 kilometers. One other strict question that they always ask during GCE is, an object has a speed of 160 kilometers per hour. What does this mean? What does this mean? So this means the object or the body, whatever they call, this means it covers a distance of 160 kilometers in 1 hour. That's the expression. So, for example, a train has a speed of 160 kilometers per hour. What does this mean? So this means the train covers 160 kilometers in 1 hour. Okay. Let's look at displacement. We have talked about distance. Displacement is the distance traveled in a specific direction. So the distance traveled in a specific direction is what we call displacement. So if you want to talk about displacement, you talk about a car, for example, or a person moving 500 meters and they give the direction. For example, due west, due east, and so on. So with those expressions added to distance, it gives us what we call displacement. And displacement is equally measured in meters. Now, what's the difference between distance and displacement? Distance is a scalar, while displacement is a vector quantity. So therefore, since displacement must always have a direction, it is a vector quantity. Okay? So that's why it's a vector quantity. And then velocity is the rate of change of displacement. Velocity is the rate of change of displacement, or the displacement per unit time. And since displacement is a vector, velocity is equally a vector because velocity has direction, magnitude as well as direction. And the formula for speed and velocity is just the same. So you just change displacement to distance to displacement, and you change speed to velocity, and you do the same. So mathematically, we have velocity equals displacement divided by time taken. Okay. Scalars versus vectors. In the GCE, we always ask, give the difference between a scalar and a vector. Give two differences and so on. So what are scalars? Scalars are quantities that have magnitude but no direction. So scalars are quantities with magnitude but no direction. Okay, it has only magnitude. While vectors have both magnitude and direction. So with vectors, we have magnitude and we have direction. Examples of scalar quantities include time, distance, speed, mass, volume, density, area, and so on. While examples of vector include displacement, velocity, acceleration, force, momentum. So all these are vector quantities: displacement, velocity, acceleration, force, and momentum. So what are the similarities between scalars and vectors? At times they'll say you give the similarities and also give the differences. The similarities is that they both have magnitude and they are both measured in units. Okay? So that's where we round up with that. We now move to motion. The types of motion there are. There are three types of motion. There are three types of motion. We have straight line motion, also known as linear, rectilinear motion. We have circular motion and vibrational motion. This vibrational motion is also called oscillatory motion. Vibrational motion is also called oscillatory motion. So, let us start by looking at straight line motion. Let's start with straight line motion. So, straight line motion is the motion in which an object moves along a straight line. That is, the direction does not change. So, straight line motion is the motion in which an object moves along a straight line. For example, a stone that is dropped from a height h is undergoing what type of motion? It's undergoing linear motion. Equally, a car traveling along a straight road is undergoing linear motion. You can say linear rectilinear motion. And with a motion on a straight line, it can be further divided into two. You have uniform straight line motion and accelerated straight line motion. So we have linear motion being divided into uniform straight line motion and accelerated straight line motion. When you talk about uniform straight line motion, means that the object is moving with a constant velocity. So the speed or the velocity of the object is constant. Well, the emphasis here is the velocity is constant. Because if the velocity is constant, then the acceleration will be 0. Okay? Now, with accelerated straight line motion, the speed is the object is either speeding up or slowing down. It's moving on a straight line and it's either speeding up or slowing down. For example, when you drop a stone from rest, what happens? The speed increases, continues to increase, so the object is accelerating as it falls on a straight line. And then, for example, to a car moving along a straight road that is slowing down is undergoing accelerated motion. So the acceleration can either be positive or negative. So it will be positive if the object is speeding up, is accelerating, that is speeding up, or slowing down if it is decelerating. So uniform straight line motion is either linear straight line motion is either uniform straight line motion or accelerated straight line motion. Now, acceleration tells us how fast the velocity is changing with time. Acceleration tells us how fast the velocity is changing with time. If the acceleration does not change with time, then we say the object is undergoing uniformly accelerated motion. And to calculate acceleration of an object, we have final velocity minus initial velocity divided by time taken. Because acceleration is defined as the rate of change of velocity. Velocity is the rate of change of displacement, while acceleration is the rate of change of velocity. Rate of change means change per unit time. So mathematically, acceleration is given by the formula final velocity minus initial velocity divided by time taken. And since we have velocity divided by time, the unit for acceleration is the meter per squared second. So the unit for acceleration is the meter per squared second. And there is one important thing we should think, we should have in mind here. This is the unit, and the other unit for acceleration is the newtons per kilogram. If you simplify that, you are also going to end up with the meters per squared second. Okay. So acceleration can be given as newtons per kilogram. It can equally be given as meters per squared second. Though this one is the common one. We will see that when we get Newton's laws, and you see that acceleration is also given by a force divided by mass. And because of that, since force is measured in newtons and mass in kilograms, the unit of acceleration becomes the newtons per kilogram. Now let's take this example. A bike has to travel in 250 seconds. In the first 50 seconds, at a speed of 800 meters per second. And in the next 200 seconds, by 1800 meters per second. Calculate its acceleration. Calculate its acceleration. So this motion has two parts. In the first part of the motion, the object is covering 800 meters in 50 seconds. Okay, so 800 meters in 50 seconds, 800 meters per second in 50 per second for 50 seconds, and in the next 200 seconds, the velocity is 1800 meters per second. So what is the acceleration of this particle or of this object? So the initial velocity is 800 meters per second. And what's the final velocity? 1800 meters per second. So acceleration is defined as the rate of change of velocity. So this will give us final velocity minus initial velocity divided by time taken. And this will be equal to 1800 minus 800 divided by 250. So the acceleration of this object is the meters per squared second. Okay, here we have per squared second to the power 2. Please take note of that. So we have 4 meters per squared second. Now, example 2, the speed of a car changes from 150 meters per second to 80 meters per second in 7 seconds. We listen to the question again. The speed changes from 150 meters per second to 80 meters per second in 7 seconds. What is its acceleration? I would first of all like to bring in something here that they'll always ask in the GCE. In cases like this, if the speed changes from 150 to 80, is this car speeding up or slowing down? Because that the speed has reduced, right? And when the speed reduces for a car, what is happening to the car? The car is slowing down. So this car is actually slowly slowing down. And when a car is slowing down, we talk about negative acceleration or a deceleration. So whenever a car is slowing down and you calculate the acceleration, your answer must have a negative sign. So during the GCE, they'll say that you do a calculation on acceleration and you have an answer, and then they'll ask you, can you explain why the acceleration has a negative value? The explanation of this is, it has a negative value because the car is slowing down. This is a negative acceleration, or also called a deceleration. So for this car that is slowing down, the acceleration will be given by final velocity, which is 80, minus initial velocity, which is 150, divided by the 7 seconds. And that gives us negative 10 meters per squared second. The per squared second is omitted again here. Please take note, is to the s to the power 2. So negative 10 meters per squared second. And this negative sign is because the object is slowing down. And then with circular motion, it is the motion of an object in a circle or a circular path. So circular motion is the motion of an object in a circular path. Its distance from a fixed point does not change. For example, if you wheel a stone in a horizontal circle or vertical circle, this is an example of circular motion. Or the wheels of a moving car are undergoing what type of motion? They're undergoing circular motion. So there are two types equally of circular motion. Just like with linear straight line motion, we had uniform straight line motion and we have accelerated straight line motion. Here equally we have two types of circular motion, and the terms do not change. The only thing that will change is the circular. Okay, so we equally have uniform circular motion and accelerated circular motion. Why do we call one uniform circular motion and the other one accelerated circular motion? For uniform, just like previously, the speed of the object does not change, or the speed of the object is constant. For example, a very good example of this is the hands of a clock. The hands of a clock. For example, the second, it just click. It's only after every second. So what happens? The speed is constant, so it's undergoing what you call uniform circular motion. Equally, the Earth moving around the sun is undergoing uniform circular motion. Though we know that the orbitals are not actually circular, they are elliptical, that in calculations you can approximate them to circular motion. And then with accelerated circular motion, it occurs when the velocity of the object is changing, either because the speed changes or the direction of the object is changing. So objects in circular motion make what we call revolutions, like the revolution of the Earth about the sun. So when the Earth goes around the sun once, we talk about one revolution. Okay, so when the Earth goes around again another time, we have to talk about another revolution, goes again. So a revolution is the term used to describe the motion of objects in circular paths. Then the acceleration of the object is directed towards the center of the circle. For objects which are undergoing circular motion, their acceleration is always directed towards the center of the circular path. So the direction of the acceleration is always towards the center. And if the acceleration changes direction, then the object should normally skid or move away from that path. It should skid. For example, if you're whirling a stone in a circular path using a string, right? What happens when the string breaks? The stone no more goes round in that circular path. The stone changes direction, right? It now follows a linear, maybe straight line motion direction. That is because its acceleration is no more directed towards the center because the string breaks. Now, what is a revolution? A revolution is a complete cycle or oscillation. So a revolution is one complete cycle or oscillation. Now we look at vibrational motion or oscillatory motion. So vibrational motion is defined as the to and fro movement of an object, the repeated to and fro movement of an object. To and fro means forward and backward. So the repeated forward and backward movement of an object is what we define as vibrational motion or oscillatory motion. Such an object is said to be vibrating. You know about these machines that they use to dampen roots, right? They are actually vibrating. Another example of a very good example of vibrational motion is a swing. Most of you sit on the swing and then your elder brother or younger brother is pushing, you move forward and backwards. So that is vibrational motion. Another one is a simple pendulum. A simple pendulum is like when you tie a bulb or a mast to a string and you hang the string on the ceiling and then you move one end of the string. So this is an example in this diagram. So this is an example of a simple pendulum. In the GCE at times they'll say that you should draw a simple pendulum. So this is the exact diagram that you have. So for you to have a simple pendulum, you need a fixed support. This is a fixed support, right? This one can be the ceiling. Then you need a string. This is the string. Then you equally need a bulb or a mass. So these are the components of a simple pendulum. You have 1, 2, 3. So let us see what happens with the motion in simple pendulums when the bulb is displaced from its center position. When you just carry out or you just design this, you find out that the line, this string will be vertical like this and the bulb will be at this bottom position. Now if you displace it a bit, like at this position, you can now see it. If you now displace it to this position and allow it, the bulb is set into motion. So the bulb will now be in motion. And this will be the relative positions of the bulb with respect to time. So it will move from points. It was initially at A. You displace it to C and allowed it. When you allow it at C, it will move from C back to A, cross A and move to B. When it gets to B at a point of maximum displacement, it will come back to A. And from A, it will pass back to C until all the energy in it dies down. It has lost all of its kinetic energy. It will now remain back at this position A. Okay, so the mistake is you draw a simple pendulum and describe the energy changes that occur in it. So as you can see on this diagram, the bulb has come to rest at this point. It comes to rest at this point. Then at this point, the bulb is at maximum displacement. The displacement further away from, because this is the normal position when it will be at rest. So at this point it's at maximum displacement, and here is equally at maximum displacement. And the maximum displacement of an object from rest is what we call the amplitude. So its maximum displacement from rest is the amplitude. Now let us see what happens with the bulb. So at the points B and C, B is the maximum displacement to the left, C is maximum displacement to the right. The bulb is at maximum position from the resting position. So at the points B and C, it is at maximum displacement from the resting position. Look at the points B and C. So here, the bulb is at maximum displacement from the resting position. Then what happens to it? At this point, so at B and C, the bulb is at maximum displacement from the resting position. At the point B, when it instantaneously gets the point B or the point C, it will not move. immediately it gets to the point C, because that's the maximum displacement, it will not move. And what is happening? It's about to change its direction. So instantaneously stops and then reverses its direction. So at this position, the speed is 0. Let's look at the diagram again. So at this position here, the bulb comes to rest. At C, the bulb is at rest. Why? Because the speed at this point is 0. When it moves from A to C, the speed here is 0, and it has to change its direction. The speed will start increasing again, and the speed is maximum at A. So the speed is greatest at the point A, and then it comes back to B. But the truth is that at the end, when all the kinetic energy is exhausted, it is now A that will have this final speed to also be 0, because the bulb will no more be moving. So here, at B and C, the bulb is at maximum position from the resting position. That is, it is not moving. At this position, the speed is 0. This is how you answer the question, the GCE. That's outlined exactly on these notes. If the bulb is about to change its direction of motion, it stops moving for a short while, that's the instantaneous stop, before reversing the direction of motion. The bulb has a maximum speed and maximum kinetic energy at A, that lowest position. The bulb has the least speed at B and C. Whenever the bulb has the least speed, it has the maximum potential energy. And the period of a simple pendulum depends only on its length. This question is also fertile in the GCE. The period, that's the time taken for one complete oscillation of a simple pendulum, depends only on its length. It means that if you use a longer rope, because it is directly proportional, the longer the rope, the longer the time the bulb will take to move. So the period of simple pendulum is directly proportional to its length. The longer the string you use, the longer the period. That means the longer the time it will take to make one complete oscillation. Some of the terms that we encounter with vibrational motion include amplitude. The GCE will ask you to define amplitude. Amplitude is the maximum displacement of an object from the resting position. What is a vibration? A vibration is the to and fro or forward and backward movement of an object. The repeated to and fro or forward and backward movement of an object. And what is frequency? The frequency of an object is the number of complete cycles or oscillations made per unit time. And note, very important, the time must be in seconds. Whenever you have to calculate frequency in an exam, the time must be converted to seconds. So if they give the time in minutes, convert it to seconds. These are some of the mistakes that students make. So mathematically, the frequency of an object is given by the number of oscillations or the number of cycles divided by the time taken. And the number of cycles per unit time is equal to the hertz. The hertz is the same as 1/second as the hertz. Okay. Now let's take an example. Let's take an example on this. Please guys, as you are watching this video, don't forget to subscribe. Don't forget to share this video. That is the way that you are going to motivate us. And leave your comments on what you think we should do. We equally have some past questions which you have answered, which are online. Go through those past questions and see the styles in which questions are being answered. If you have a comments, leave your comments under those videos. You can visit us on www.gcemathspanel.blogspot.com, or you go to GCE PREPS with S platform. That's gcepreps.blogspot.com. You'll find us there. If you need private classes, why not contact us directly from gcepreps.blogspot.com or gcepreps.com, where we will be attending to you. Let's take an example on calculations of frequency. A vibrating object makes 300 oscillations in 6 seconds. Calculate its frequency. A vibrating object makes 300 oscillations in 6 seconds. Calculate its frequency. So frequency is calculated as the number of oscillations per unit time. So frequency will be equal to 300 oscillations divided by 6 seconds. And the answer should be in hertz, because frequency is measured in hertz. And time must be in seconds for you to write the hertz. If the axis is calculated by the period is the reverse of this formula, the inverse. So period is the time divided by number of oscillations, while frequency is the number of oscillations divided by time. Do not make a mistake with this formula. I think that you should master one, so that if they ask the other one, you should know that it's the other one that you did not master. Now, example 2, a body makes 100 oscillations in 25 seconds. Calculate its frequency. So frequency is number of oscillations divided by time. So we'll have 100 divided by 25. That will give us 4 hertz. Okay? 4 hertz. If they ask of the period, you will take 25 seconds divided by 100. And what would that give us? 0.25 seconds. Because period is measured in seconds. Period is time. It's measured in seconds. Exercise. A pendulum makes 180 cycles in 1 minute. Calculate its frequency. This example is a trap. You must convert this time from minutes to what? To seconds. So your answer should be equal to 180 divided by 60. And your answer will be 3 hertz. Calculate the periods in example 1 and 2 above. So for example 1 above, the object made 300 oscillations in 6 seconds. It made 300 oscillations in 6 seconds. So the period will be 6 seconds divided by 300, or 1 divided by this 50 hertz. And what would that give us? 0.02 seconds. And for this second example, this object has made 100 oscillations in 25 seconds. So the period will be 25 seconds divided by 100, which is 0.25 seconds. That's the period. Now, period is the time taken to make one complete cycle or oscillation. And period, as I've said, is measured in seconds. So if they give you the period in minutes in your calculations to find frequency, make sure you convert. Make sure you do the conversion. So the formula for period is equal to the time divided by number of oscillations. All right, let's take this other example. Let's take this example. A body makes 80 cycles in 0.4 seconds. Calculate its period. A body makes 80 cycles in 4 seconds. Calculate its period. So period is equal to time divided by number of cycles or oscillations. That will give us 0.4 divided by 80. And you have your answer in seconds. Okay. Now, example 2. Two bodies A and B are oscillating as follows. A makes 200 oscillations in 50 seconds, while B makes 100 oscillations in 50 seconds. So they are both 50 seconds, right? Calculate the periods of A and the period of B and say which has a greater period. So let's calculate their periods. So the period for A will be 50 seconds divided by 100 by 200 rather. That gives us 0.25 seconds. And for B, the period will be 50 seconds divided by 100, and that gives us 0.5 seconds. So which one has a bigger period? So B has a larger period, which is 0.5 seconds. Okay. Now we have the relationship between frequency and period. The relationship between frequency and period. From above, frequency is equal to 1 over period, and period is 1 over frequency. For example, a vibrator has a frequency of 50 hertz. Calculate its frequency. A vibrator has a frequency of 50 hertz. Calculate its frequency. So since this is its frequency, calculate its period. So the frequency is 50, the period will be 1 over frequency, which will be 1 over 50 hertz. And that gives us 0.02 seconds. Okay? Alright, now let's look at some questions on this chapter. How can someone make a simple pendulum? State the 3 types of motion and what's the difference between uniform linear motion and accelerated linear motion. What is the difference between speed and velocity? What's the difference between displacement and distance? What's the difference between accelerated motion and uniformly accelerated motion? What is the unit of speed, distance, time, frequency, period, acceleration, velocity, and so on? This is the introductory chapter. Don't forget to subscribe, guys. State the formula of the following: speed, acceleration, frequency, distance. Then here we have a machine oscillates at 1800. Okay. On chapter, let me go back to the chapter. I think I skipped this one. Yeah. Alright, so a machine oscillates at 18,000 times in 2 minutes. Calculate its frequency and period. Then calculate the speed of a car covering 500 meters in 25 seconds. These are mostly multiple choice questions. What is the period of a machine that has a frequency of 4 Hz? What happens to the period of a simple pendulum if the length of the rope is doubled? I will answer this one. As we said, the period, what happens to the period of a simple pendulum if the length is doubled? You said the period of a simple pendulum depends only on its length, right? Or the frequency depends only on the length. So if the period is doubled, what happens to the length? Alright, you leave your comments below. If the mass is increased, what happens? You already know the answer to this one, right? Also leave your comments below. Now draw a simple pendulum and label it. Define motion. Okay, guys, this brings us to the end of chapter 1. Now in chapter 2, we'll be looking at scalars and vectors. We'll be looking at scalars and vectors. So what is a scalar? A scalar is a quantity that has only magnitude and no direction, as we discussed before, while vectors have both magnitude and direction. And you can use this table like this to differentiate. In this topic, we'll be focused on forces. A force is a pull or a push on an object by another object. So simply, a force is a pull or a push on an object, normally by another object, right? Okay, so but it can be by another, something might not necessarily be an object, maybe because it can be due to a field and so on. So a force is measured in newtons. So the SI unit for force is the newton. Okay. So for example, a push of 10 newtons is a force, a pull of 150 newtons is a force, and so on. And they always ask also for the effects of forces. What are the effects of forces? Forces can cause an object to start moving, or forces can cause objects to start moving. Forces can stop the motion of moving objects. Forces can increase or decrease the speed of moving objects. Forces can change the direction of moving objects. Force can change the shape, e.g. squeezing an orange. Okay, so the effects of forces are they can set objects into motion, they can stop moving objects, they can increase or decrease the speed, they can change the direction of moving objects, and they can equally change the shape of an object. And forces always act in groups, equal and opposites. They act in groups which are equal and opposites. From Newton's law, talk about action and reaction, which are equal and opposite. Let's look at the different type of forces that we have. Generally, forces are grouped into two. Forces are grouped into contact and non-contact forces. Contact forces and non-contact forces. Let's start with contact forces. A contact force is a force that acts only between objects which are in contact. So this force only acts when the objects are in contact. For example, friction. Friction is a contact force. And friction is that force that acts between our shoes and the ground, between the car and the road and so on. So this is one of the contact forces. We look at other contact forces here, but we will start with friction. Okay. Even tension is another contact force. The object should be in contact for friction to act. So what is friction? Friction is the force which opposes the relative motion of objects which are in contact. Friction is that force that opposes the relative motion of objects which are in contact. What are the advantages of friction? Friction has advantages as well as disadvantages. So for the advantages of friction, we have it helps moving objects to slow down. Friction helps moving objects to slow down. Friction also helps objects to start moving. Without friction, it will not be possible for somebody to move, because when you try to stand, your legs will just keep sliding and will not be able to stand. As well as its disadvantages. Friction produces unwanted heat in moving part of machines. And this heat like this has been the cause of fires and other things in the electrical and other industries. Friction also reduces the efficiency of machines, because it makes all the power that is supplied is not being used. Some are wasted due to friction. Friction wears away surfaces. For example, you buy a new Christmas shoe and you wear it for 1 or 2 weeks. By the time you look at the shoe under, friction has already cleared some part off. So friction wears away surfaces, and friction reduces the speed of moving objects. So the more you try to move, the more friction tries to stop you from moving. This finally brings us to ways in which we can reduce friction. So we can reduce friction by using oil or lubricant. We can reduce friction by using oil or lubricant. Then by the use of bearings and rollers. By the use of bearings and rollers. And we can also reduce it by smoothing. We can also reduce friction by smoothing. The next contact force is tension, which I mentioned. So tension is that force that acts on stretched materials like strings or rubber bands, causing elastic materials to expand depending on the force applied. So tension is that force that acts on stretched materials like strings or rubber bands and causes elastic materials to expand or contract depending on the force applied. This brings us to what we talk of, which is Hooke's law, which states that the extension of a spring is directly proportional to the applied force. So the extension of a spring is directly proportional to the applied force. And in ordinary level, this definition is not complete. You have to add something here. That's why I left it like this. So Hooke's law states that the force applied to an elastic material, this is how you have to say it during the GCE. The force applied on an elastic material is directly proportional to its extension, provided there is a condition, provided the elastic limit is not exceeded. So Hooke's law states that the force applied to an elastic material is directly proportional to its extension, provided the elastic limit is not exceeded. Let's look at this diagram, which is on tension. So if you look at this mass which is placed on this this pan, we have this spring and we have this support. So the more you add masses on this tray or this pan, the more this spring will extend and the more this will move downwards. Position will keep on moving downwards. And this is a meta rule. You can get the extension. Now for this spring, the unstretched length is called the original length, L0. So when the string is not loaded, we talk about its original length. And we can get the extension by taking the new length minus the original length. For example, let me say the original length was 1 meter when no load was on the pan. Now, when we now put a load of 1 kilogram, it moves to 1.1 meter. So what has been the extension? The extension is 0.1 meter, which is 1.1 meter minus 1 meter. We will look at more of this in part 2. So let's look at this example. Sometimes also you are given a table like this and you be asked to calculate maybe the extensions. So here, when there is no load, when the load is 0, that is, load means weight or mass. You have the natural length of the spring. And the extension is always equal to 0 when the tray or the pan is not loaded. Now, when you add a load, for example, 1 Newton, or let me say you add the first load, the length increases to L1. And now, what will be the extension? The extension will be L1, this L1 here, minus L0. L1 minus L0. If you add another load, the length moves to L2. The new length is L2. And what will be the extension now? With respect to L1, it will be L2 minus L1. But considering the extension from the original, we are going to have L2 minus L0. The third one, L3 minus LL0. So if you have to get the extensions, corresponding extensions in this form, that is progressive extensions, and then we work with it this way. As I've said, we'll look at more of this in part 2. Now this is a graph, a force extension graph for an elastic material. This is a force extension graph. This axis is the force axis. This axis is for extension. So it is a straight line until this point. This is the elastic limit. After the elastic limit, the graph is no more a straight line. After the elastic limit, it's no more a straight line. And here you have the breaking point. So if you put load until to a certain limit above the breaking point, what will happen? The spring will break, or it will lose its elastic properties and become plastic. Cannot go back to its original length after the loads are removed. That's why sometimes some strings now, the strings they were not very lengthy, but because they have been continuously loaded, and that's what happens. Like some of these pan balancers they use in the market, after using for a very long time to get it to weigh and so on, you find out the spring keeps on extending. And at times now, maybe they'll put something, you go to buy, they put something that's not up to 1 kilogram, but the spring will now show 1 kilogram when maybe 0.8, and they use that in cheating in the market. Please don't use these videos to cheat in the market. Thank you so much. So this graph shows how the force is directly proportional to the extension. Okay. So when we look at the spring being proportional to the extension, there are different portions of the curve which I have not talked about. This portion like this, this is the point O, from here along this straight line O to E, is what we call the proportional section. Okay. In this region, the force is proportional to the extension. Okay. Now, above it, we move now to the region where the force is no more proportional to the extension. You look at more of this in part 2. The next contact force is upthrust. We have looked at friction, we have looked at tension. We equally have upthrust, which is also a contact force. And upthrust is defined as the upward force exerted on an object when immersed in a fluid. So upthrust is the upward force exerted on an object when immersed in a fluid. And what's a fluid? A fluid is either a liquid or a gas. So fluids are liquids or gases. And upthrust, this was measured by a scientist called Archimedes. We will talk about Archimedes' principle. Like a song that we usually sing in Form 1 and Form 2. Archimedes' principle states that when an object is partially or wholly immersed in a fluid, it displaces an amount of the fluid whose weight is equal to the amount of upthrust acting on the object. When an object is partially or wholly immersed in a fluid, it displaces an amount of the fluid whose weight is equal to the amount of upthrust acting on the object. So I will not forget to make reference to my physics teacher in GBHS Bamenda, Mr. Tata Gerald, one of the great physics teachers, which I think the government, if it's looking at teachers, this is one of the people that I think I can recommend for anything. Yes, Mr. Tata Gerald, and I equally have Mr. Chi Christopher, who have really worked so hard. There are many of them out there. I'm sorry, I'm just mentioning the ones I have come in contact with who have really done their best. They teach you as if there is no tomorrow, as if everything depends on them, as if everything depends on today. And I will not also forget to make reference to the math teacher, Madame Abongwa Julien, the only female lioness, let me just say lioness, in the mathematics field. The lady who does not only teach as a teacher, but more than a mother, who might just be passing and see that you are free, and just that I saw that people were free and you decided to come. We will sigh and sigh, but at the end of the class, you attend because she is teaching happily. Alright, let's continue with the lesson. So this is Archimedes' principle. Archimedes' principle, and you can have an experiment to measure Archimedes' principle. An experiment to verify or measure Archimedes' principle. So to verify or to measure Archimedes' principle, This is how you set your experiments. Aim. In an exam, you're asked to do this, what you do. Aim to verify Archimedes' principle, or you say an experiment to verify Archimedes' principle. Requirements: spring balance, water, large beaker, object, thread, small beaker. Then now the next step is the diagram or the setup. So this is the diagram or the setup to measure Archimedes' principle. Okay. Now this one is fixed to a support. This is the support. So it's fixed to this support. That's the spring balance is fixed to a support. Okay. Then now, but before this stage, because I'm still coming to procedure, as you can see, the first thing that is to be done here is you have this Eureka can. Eureka is this type of these are the type of beakers that have this type of mouths that are pointing that water can come out. Okay. So you have this large beaker with this Eureka. Then you have this is the water that is displayed, and then you have a small beaker. This is a small beaker. You have an object. This object should not be an object that dissolves in water. Okay. So this is water now. They mostly use water. Then you have a thread. This thread is attached to the object and then to the spring. The assumption in this experiment is that this thread, the weight of this thread is negligible, or the mass is negligible, everything. That brings us now to the procedure. Let's see how this works. So we first of all weigh the object in air. So we first of all weigh this stone in air. That is, we weigh it freely, not putting it inside anything. We note the weight as W1, that's the weight in air. We now put water inside this Eureka can until it flows out. Put it until it starts flowing out, and then you stop. They allow it to flow out until it's at this level now, but nothing is flowing out anymore. The water is now stationary. Then you gently, what you do is you gently lower this mass now into this water. The mass, remember, the mass is still suspended on that spring balance. You gradually lower it. At that time, before you lower it, this small beaker should be empty before you lower it inside. Okay, this small beaker should be empty. Then you get the weight of this empty small beaker. The weight of the empty small beaker. Okay, so you weigh this empty small beaker first, then you now place it here. After this water has come out, you place at this point. No water will drop inside. Then you now gradually lower this bulb inside this can, and in lowering it, it should still be suspended on this spring balance. Lower it gradually. Okay, when you lower it now, you will now read the new reading of the weight of this object now in water. You already have the weight in air, which was W1. Now we have the weight of the object in water. Its weight now in water should be W2. You read the weight in water now, W2, what the mass, the spring now shows. Then equally for the small beaker, the weight of this small beaker when it was empty is W3. And now when the water flows inside, the weight of the water plus the small beaker is what we call W4. So we now see from this point that this weight of water plus beaker minus W3 gives us just exactly the weight of the water. Okay. And then now we have the weight of the stone in air and the weight of the stone or object or whatever in water. Now what's the observation? Your observation will be that you will see that W4 minus W3 will be equal to W3 minus W2 minus W1. That is the weight of the stone in air minus the weight in water will be equal to the weight of the beaker plus water minus the weight of the empty beaker. So this is what you're going to see. So W2, W1 minus W2. So the weight of the object in air minus the weight in water will be equal to the weight of the beaker plus water minus the weight of the empty beaker. So what is the conclusion? The upthrust force is equal to the weight of the water displaced. And this brings us now back to this definition of this song that we just sang. What does Archimedes' principle state? It states that when an object is partially or wholly immersed in a fluid, it displaces an amount of the fluid whose weight is equal to the amount of upthrust on the object. This is how we verify Archimedes' principle. For this note, please, you can get to www.gcemathspanel.blogspot.com and you'll get the notes there, or you go to gcepreps.blogspot.com and you have the notes there. Then for non-contact forces, a non-contact force is a force that acts between objects that are not in contact. A force that acts between objects that are not in contact. Please join us for our GCE past paper corrections online. There are equally videos and our GCE preparatory classes online. You can get to us on WhatsApp on the numbers that are below this video, and going to those blogs you find our numbers there. You can join our WhatsApp groups for preparation. If you need private tutoring, please contact us immediately. There is no time. Full-time tutoring. Magnetic force is one of the first examples of non-contact forces, and this is the force that acts between magnets and non-magnets, or the force that acts between a magnet and a magnetic material. So the force that acts between a magnet and a magnetic material is what we call the magnetic force. It can also act between a magnet and a magnet, or a magnet and a magnetic material. It cannot act between a magnet and a non-magnetic material. So you can use this idea to distinguish between three objects in which they say one is a magnet, the other one is a magnetic material, and the other one is a non-magnetic material. So from there, you can use this idea to check, to determine which of the objects is a magnet. Alright, so if you have three objects A, B, and C, one is a magnet, one is a non-magnetic material, one is a magnetic material, what you do is you bring the objects together. Or you take A, you first bring it close to C and to B. If any of the two objects attract each other, then it means that one is a magnetic material. So for the two that attract each other, you now take these two, the other one that does not attract any of them. Okay? That does not attract any of them. When you brought all the three together, nothing, it does not attract any of them. The one that does not attract, just take it away. That one is a non-magnetic material. Then you can now use a magnet to determine which of these two materials now is a magnetic material. For a magnet, when you bring a magnet, a north pole of a magnet to the north pole of the other magnet, north-north will repel. But if the other object is just a magnetic material, if you bring it to any of the sides of the object, only attraction will occur. We will equally see this again in part 2. Now, a magnet has two poles, the north pole and the south pole. And the law of magnetism states that like magnetic poles attract and unlike magnetic poles attract and like magnetic poles repel. Okay, yes, this is supposed to be repel. So, like magnetic poles repel, please take note of this. Like magnetic poles repel and unlike magnetic poles attract. Thus, the north pole will attract the south pole, but will repel the south pole. So this means that north-north is repel. They'll repel, but north-south. So the north pole will attract the south pole, but the north pole will repel the north pole. Okay, I think this is a typo again. Let's now look at electrostatic force, which is another non-contact force. So this is the force which acts between charged objects, e.g. a charged cork can attract pieces of paper. We did this experiment in take the cork of your pen, you rub it on your hair, rub it, and then you bring it very close to very tiny pieces of papers, and you start going to pick those pieces of papers. This is what this thing is saying here. The force that acts between charged objects, e.g. a charged cork can attract pieces of paper. Don't go and take it. Don't take it to a big piece of paper. The force is too small to attract that big piece of paper. So electric force, like magnetic force, can be repulsive or attractive. Now, the one difference with a gravitational force is that gravitational force is only attraction. Now, electrostatic force is a non-contact force. Magnetic force is a non-contact force. For electrostatic force and magnetic force, they both have attraction and repulsion. But for gravitational force, which is also a non-contact force, we only talk about attraction. The force of gravity only works with attraction, it does not repel. So the gravitational force is defined as the downward pull of the earth on an object. You can start only pull appears here. The downward pull of the earth on an object. And all objects on earth experience this force. This is why Objects that are released from any position they fall downwards. You hardly see something falling upwards. Maybe air resistance can be greater than the weight of the object, and then the thing has to move upwards. Yes, the gravitational force still acts on the object, just that the upward force on it is greater than the downward force. In that case, the resultant force is upwards. A downward pull of 10 newtons on 1 kilogram of any object on Earth. It's an example of this. So the gravitational pull on Earth is 10 newtons per kilogram. They can ask, what does this mean? It means that each object, or an object of 1 kilogram, experiences a pull of 10 newtons. Experiences a gravitational pull of 10 newtons. And this gravitational pull, as we have said before, newtons per kilogram is also acceleration. So instead of talking about gravitational pull, we can talk about the gravitational acceleration. Times the axis to draw an object and name all the objects, the forces acting on it. Okay, so you gotta have revision. Please go through this revision on this chapter from the blog www.gcemathspanel.blogspot.com or gcepreps.blogspot.com. If the blogspot is having issues, then you go directly to gcepreps.com or gcemathspanel.com as we upgrade our systems. When two forces F1 and F2 act on an object along the same line of action, we may have the following results. So here we are looking at resultant forces. When two or more forces act on an object, there will be a resultant force, right? Like if a car hits a trailer, a small car hits a trailer, there should be a resultant force. So now let's look. If two forces F1 and F2 act on an object along the same line, this is the line of action, then the following may result. If they act in the same directions, look at F1 and F2, they're acting in the same direction, right? So the resultant force will be F1 plus F2. So this F1 and F2 can be on the same side or on opposite sides. In this first case, they're on opposite sides. In the second case, they're on the same side, like two boys pulling this thing. Or in this first case, one boy is pulling, the other one is pushing. So the resultant will be the sum, because it's in the same direction. So in the same direction, we sum it. Now, if they act in opposite directions like this, opposite directions, then the resultant force will be in the direction of the bigger force. Like when people are doing a tug of war, people are pulling a rope, this one is pulling this direction, this one is pulling the other direction. The people that are more powerful, the rope will end up moving in their direction. The resultant is in their direction. That's an example. Okay. So, for example, here you may equally be having like this second case. Like, for example, somebody is pushing you out of the house and you are forcing yourself inside. Their direction will end up being the direction in which the force is stronger. Now, if the two forces act in opposite directions and have the same magnitude, look at this case. They act in opposite direction, the magnitude is the same, then the resultant force will be 0 because the object will not move. Let us look at some calculations, some examples. Here we have these 40 newtons and this 200 newtons acting on this object. This 200 newtons is greater, right, than these 40 newtons. But what about their directions? Directions are the same. They're all acting towards the right. So the resultant is the sum. We have 40 plus 200, which is 240. In this second case, you equally have the two forces acting, but they are acting in opposite directions. The resultant should be in the direction of the force that is greater. So it should be to the right, because this 6 newtons is acting towards the right. The direction is to the right. So the resultant force will be like this, 4 newtons to the right. Now for this third case, we have two forces acting. They're acting on the same side of this object, but their directions are also the same. So the resultant will be the sum. While for this case, they are on the same side, but their directions are opposite. So the resultant will be in the direction with the greater force. So the resultant force will be 4 newtons to the left. Now let's look at these exercises. We have all of this. The resultant force should normally be how many newtons? 10 newtons to the right. Here, 420 newtons to the right. Here, 16 newtons to the right. This one, 248 plus 18, that's 258, 266 newtons to the right. Now with this one, directions are opposite. The greater force is towards the right, so the resultant force should be 52 newtons the right. Okay, and then with this, here they want us to find x. I like this question. Look at this one very well. So now, a force of 100 newtons acts to the right and x newtons acts towards the left. The resultant force in the system is 80 newtons. Find x. So if the resultant force is 80 newtons and is to the right, it means that this 100 newtons is 80 newtons greater than this x. So we just have 100 minus 80. That gives us 20 newtons. So x is 20 newtons. And you can put inside here and you see that the answer is 20 newtons. Because 100 minus 20 is this 8, which is the resultant force. And then here, the object will not move, right? Because we have 30 newtons to the left, 30 newtons to the right. So the resultant force is 0. What about this case? The resultant force here also will be to the left. And that will be 70 newtons minus 20 newtons, which is 50 newtons. Now here we equally have more examples. My interest is on this one. Look at the resultant forces here. We have some forces acting this to the right, some to the left. So how do we get the final resultant force on this object? So Pythagoras theorem may find itself here. Okay, so now we have 80 newtons to the right and 70 newtons to the left. Let us omit this force that is not mentioned. Let's leave it out. Okay, so now with this, we are going to have the resultant force here will be 10 newtons to the right. And with this other one, with the forces acting upwards, we have 100 plus 20, that's 120. So this will give us a right angle triangle. And the resultant force will now be given by Pythagoras theorem. Please check on our classes, PREPS classes. We answer most of these questions live, but here we are explaining the lectures. This is a good example of that last case which I'm talking about. So what does this one show? It shows that two forces of 4 newtons and 3 newtons should be arranged such that the resultant is alright. So how can, if you are given two forces of 4 newtons, this is a partial equation, and 3 newtons, how can you arrange these forces so that the resultant is 7 newtons? For 7 newtons, the two should act in the same direction. If the resultant has to be 1 newton, then they have to act in opposite directions, right? And if you want the resultant to be 5 newtons, then they should act at right angles. So one should be acting, let me say, upwards, and one acting to the right. And the resultant force will be given by Pythagoras theorem, which is 4 squared plus 3 squared, the square root of that. That will give us 5. So this one is one that many students do not have the answer, how you can arrange, and this paper 2. So this chapter 2 ends with stability and balance. Stability is the ability of an object to remain balanced and not fall or shake. Stability is the ability of an object to remain balanced and not fall or shake. E.g., standing on 2 legs, you are stable. Now, with this stability, if a small force pushes the thing, you will still be standing. For example, you are standing and a child comes and pushes you. You can still stand. You can just shake a bit and you will just be standing. But with balance is just like you take your pen and you struggle until you place it using that is cock to be standing vertically. If somebody blows it will fall, right? In that case, so that the cock is just balanced. It's not stable. Stability means that it can resist toppling or falling. But balance means that any slight small force will just topple it over. So balance is the ability of an object to put an object somewhere so that it cannot fall, e.g. moving across a rope or river. Like all of these guys that will walk on the rope, they're actually doing what they call balance. They're not stable because they have to be shaking their hands to get balance. Unlike you that you are just standing, you are actually balanced because you don't need to use any additional energy or tactics to remain where you are. Now, equilibrium for an object is when the forces acting on it are balanced and the resultant force is 0. So like the examples you have seen before, when the resultant force of an object is 0, say it's in equilibrium, and the object is can be static. You have two types of equilibrium. You have static equilibrium and dynamic equilibrium. So when the resultant force is at 0, because an object can be moving at constant acceleration, in that case at constant velocity, right? If you move at constant velocity and then the acceleration is 0, so the force now will be equal to mass times acceleration, which will give us 0. The object is moving right, but the resultant force is 0. Okay, so the force on it is 0 because the acceleration is 0 actually, but it's moving. Then the similarity between stability and balance, both are in the state of rest. That's the similarity, and then with the difference. With stability, the object cannot easily fall, while with balance, the object can easily fall. An object that is balanced can easily fall, but an object that is stable can not easily fall. With equilibrium, we have 3 types of equilibrium. We have stable equilibrium, unstable equilibrium, and neutral equilibrium. So stable equilibrium is when an object is in stable equilibrium if it does not fall over when slightly displaced. For example, look at this first block. If you slightly displace this block, it will not fall. Now, unstable equilibrium occurs when an object falls over when slightly displaced. So this second case is unstable equilibrium. If you slightly displace this block, it will fall or topple over. While for neutral equilibrium, the object is neither unstable nor stable, and this applies to most spherical objects, like a ball. When a ball is on the ground, is neither stable nor unstable. So let's look at these examples and describe the type of equilibriums that we can find. Alright, so you go through, describe the equilibrium, the different ones that you can find. As I've said, these notes you can get them from gcematpanel.blogspot.com. And this is part 1 of 2 of this complete revision. Please don't forget to subscribe to our channel, for we still have more for you. You can join us for online live answering of past questions. You can equally join us through our WhatsApp groups, or if you need a private tutor, you can equally contact us. Turning effects of forces. You always see these questions on the first questions on your question papers. When a force acts on an object at a fixed point, which is also called a pivot or a fulcrum, it produces a turning effect. This effect depends on the magnitude of the force and the pivot's distance. This is clearly seen on a seesaw. So what is the moment of a force? The moment of a force is the turning effect of a force about a point. So we define the moment of a force as the turning effect of a force about a point. And moment is equal to force times perpendicular distance from that point. Okay? So the moment is the product of the force and its perpendicular distance from the point of application. Center of gravity. We will see more of moments in part 2 when we get to mechanics. Okay? Center of gravity of an object is the point where its weight seems to act, where all the weight of the object seems to act. That's where the center of gravity is. For example, when you are to carry a log of wood on your head, you cannot just place any point on your head. You will look for that point where the log will not be easily tilted. Else, you will be dancing with the log while moving. So you normally look for that center of gravity of the log of wood or bucket of water or whatever and put the head there. You cannot come to the edge of the bucket and then you put on your head. You'll be walking left, right, and the end you'll just be pouring the water. So the center of gravity is that point where the weight of an object seems to act. All the weight of an object seems to act. So with this, the point where the log of wood is balanced on your head is that one we can refer to as the center of gravity. Note that different objects have different centers of gravity. However, the center of gravity of most objects is at the center. This is a revision on this chapter. In the next chapter, we are moving to density. Density, please subscribe and look at the next short video, which is still in this complete GCE PREPS part 1. Complete GCE PREPS part 1. We have decided to divide the videos a bit. Complete GCE PREPS part 1. So please go through density, and thank you for watching and for staying tuned.